In the last video, we derived the equations of motion for a 2R robot. In this video, we focus on the velocity product terms c of theta, theta dot. In particular, terms that have the square of a single joint velocity are called centripetal terms. Terms that have a product of two different joint velocities are called Coriolis terms. To gain some intuition as to the physical meaning of these terms, let's continue to use the 2R arm. To focus on the velocity product terms, let's assume that gravity and the joint accelerations are 0. Then the force needed to move mass 1 is F1 equals m1 times the xyz linear acceleration of the mass. We can write these accelerations in terms of joint 1's velocity and acceleration, as you see here, where c1 means cosine of theta 1 and s1 means sine of theta 1. Notice that there are joint velocity squared terms. In other words, zero acceleration of the joints does not mean zero acceleration of the mass in the linear coordinates x, y, and z. We could do the same thing for mass 2 and get this expression for F2 in terms of the joint velocities and accelerations. C12 means cosine of theta 1 plus theta 2, and S12 means sine of theta 1 plus theta 2. Now let's put the robot at theta 1 equal to 0 and theta 2 equal to pi over 2. At this configuration, the velocity product acceleration terms for mass 2 are given here. Now consider the case where theta 1 dot is positive, but theta 2 dot is 0. Then the mass travels around the circle with its center at the first joint. The centripetal acceleration of the mass is proportional to theta 1 dot squared toward joint 1. Without that centripetal acceleration, the mass would fly off in a straight line tangent to the circle. Also notice that the line of acceleration of mass 2 passes through the first joint, and therefore the line of force needed to create that acceleration creates no moment about joint 1. So joint 1 does not have to apply a torque at this configuration and velocity. Joint 2, on the other hand, has to apply a positive torque to keep the mass moving on the circle. Next, consider the case where theta 1 dot is 0, but theta 2 dot is positive. Now the mass travels around the circle with its center at the second joint, and the centripetal acceleration is proportional to theta 2 dot squared. Finally, consider the case where both theta 1 dot and theta 2 dot are positive. In addition to the centripetal accelerations, there is now a Coriolis acceleration toward joint 2. Mass 2 times this Coriolis acceleration is a force that creates negative moment about joint 1. In other words, to keep both joint velocities constant, we must apply a negative torque to joint 1. If zero torque were applied to joint 1 would accelerate. This is what happens to a skater in a spin when he pulls in his outstretched arms. Since his inertia decreases, his spinning velocity increases. In summary, we can write a robot's equations of motion this way, but we can also write the velocity product terms as theta dot transpose times gamma of theta times theta dot. I personally like this way of writing the velocity product terms as it emphasizes the fact that the terms are quadratic in the joint velocities. Also, it emphasizes that gamma of theta depends only on the joint values theta. You can think of gamma as a three-dimensional n by n by n matrix whose entries are called the Christoffel symbols of the mass matrix. Viewed this way, gamma sub I is an n by n matrix constructed of components gamma I, j, k. The Christoffel symbols gamma I, j, k are calculated from derivatives of the mass matrix with respect to the joint variables, and the velocity product vector can be calculated as shown here. Although this looks complex, the main point is that the velocity product term can be written explicitly as a quadratic in the joint velocity vector. Just keep in mind this simple example. A mass m with a scalar velocity x dot has a scalar momentum p. The force acting on the mass is the time derivative of the momentum. If we assume the mass is constant, then F equals mx double dot. If the mass changes with the configuration, though, as it does for an articulated robot, then by the chain rule for derivatives, the time derivative of the momentum has a term depending on dm dx, the derivative of the mass with respect to the configuration. dm dx plays the same role as the Christoffel symbols of a mass matrix. Back to our list of ways to compactly represent a robot's dynamics, another common way to write the velocity product term is to express it as the product of a Coriolis matrix and the joint velocity vector. The element Cij of the Coriolis matrix can be constructed from the Christoffel symbols and the joint velocity vector. Finally, we sometimes lump all the terms not dependent on theta double dot into a single vector, h of theta, theta dot. To any of these forms of the equations of motion, we can add the joint forces and torques needed to create a desired wrench F-tip at the end effector. Now that we have a better understanding of the velocity product terms, in the next video we'll focus on the mass matrix.